Earlier we spent about 4 lectures discussing about parametric curves. So, we looked at interpolation curves like Hermite curves, and also we looked at approximation curves which include Bezier curve, B-spline curve, and also we extended that to the definition of knobs. Okay. Now, from today onwards we will be discussing surfaces, that is parametric surfaces. After having studied curves, understanding surfaces is not really difficult, because most of the definitions which we studied as a part of curves can be directly extended to surfaces also. So, that we will see as we go along. What I will do is in the beginning of this course we looked at parametric representation of curves and surfaces. So, even with surfaces you have all the 3 representations which are available, like I can define a surface as an implicit surface. So, here is a simple implicit form of a surface. You know what this surface represents. So, it is a sphere with center at origin and radius as r units. Here is another example of z is equal to function of x y, which is an explicit form of surface. So, this is a simple plane equation which is there, or I can also have like a parametric representation of the surface which is shown here. We have earlier discussed that if x, y, z are function of a single parameter, it is a curve. If they are functions of 2 parameters, then it is a surface. So, here you have an example of x, y, z, which are functions of 2 parameters u and w, and you also know what this particular equation represents. Okay. So, this represents if I have a variation of u and w, I get a cylindrical surface. Okay. Again with this thing, like axis of the cylinder is along the z axis, and whereas radius of the cylinder is r units, which is shown there. And parametric surfaces are also bound, like you try to give bounds for u and w. So, if I say, if I put bound for u as 0 to 1, then I get a complete cylindrical surface, one complete circle. If I put, let us say value of w also as 0 to 1, then you also know what is the height of a cylinder. So, this goes from 0 to h. So, h is the height of cylinder which is there. But we will be discussing primarily parametric surfaces in this particular case. But before I do that, there is one specific you can say an implicit form of surface equation which is of interest, is called as quadric surface. Now, what is a quadric surface? Like if I have an equation like this, what you are seeing in this equation is that you have all the terms which up to like a degree of 2. So, if I have x, y, z are the you can say the Cartesian system, then you have terms like x square, y square and z square. I have terms like x y, y z and z x. I also have x term, y term and z term and constant term. Now, this type of equation is, you can say an extension of having only a linear equation. Okay. If I look at, for example, only x, y, z and constant term, it represents a simple plane equation. If I extend it to one more higher degree, then this is called as a quadric surface. In fact, it represents a family of surfaces. It is not a single, depending on whether these coefficients a, b, c, d up to k, if they meet certain conditions, if depending on the conditions, it can be used to represent any of the many of the surfaces, not only surfaces, even one can look at other entities. For example, it can be used to represent a plane, or it can be used to represent two planes which are either parallel or intersecting. I can use this to represent a line. it can be a cylinder or cone, it can be just a point, or it can be ellipsoid, paraboloid or hyperboloid. So, variety of surfaces can be represented. This is also used extensively in many of the CAD applications, where I use a quadric surface to represent a family of surfaces in many cases. But as I said, this is just one of the implicit form of surfaces which we are using, and you can also extend it to cubic, but that is of not much interest in at least as far as I know. Now, coming to the parametric surfaces, now how do you define, let us say, a parametric surface is of our interest here? It can be done in number of ways, like how do you construct a surface, or how do you model a surface, how do you mathematically represent a surface is what is of interest here. Let us start with surfaces of known form. Okay. We are familiar with these surfaces, we know what a plane surface is. This also like when you say a known form, the form is also known. For example, a plane surface has a known form called flatness. Then you have a cylindrical surface which has a form, known form called cylindricity. Then you have a conical form which is called as, sometimes called as conicity, and you also have a spherical surface which represents a form sphericity, and there is a toricity which is a toroidal surface. So, these are like some of the very standard known forms of surface, which are also studied in explicit and implicit form in courses like coordinate geometry or 3D geometry or solid geometry when they are taken up in schools and colleges. Now, I think you are familiar with all of them. I do not know whether you are familiar with toroidal surface. Okay. A toroidal surface looks like this. Okay. So, this is a torus. It looks like as if you have a rubber tube which is filled with air. So, whatever is the surface which is representing is a torus. This also has two parametric directions. One parametric direction is this, another parametric direction is shown. So, the parametric lines are also shown for a torus. Now, these 5 surfaces standard known form, in fact, you will find in many of the component geometries. Usually, whenever we try to design a component geometry, we see that it has features which are a combination of these known forms only, because they have a direct relation with manufacturing. They can be very easily realized, they can be easily produced by any of the manufacturing processes. Okay. So, that is why they are also known form. Or when one goes for, let us say, an inspection, things like CMM using a coordinate measuring machine, you too have these known forms as features which can be measured, like I can measure cylindricity, I can measure toricity, I can measure flatness, which are known forms of this. So, one of the ways to define parametric surfaces is what we know is the known forms of surface. Then probably one of the most important way to define a parametric surface is what is called as a swept surface, okay, or a concept of sweeping. So, in swept surface what is done is you take a curve, okay, it can be a straight line, it can be arc, it can be any freeform curve. This is called as a generatric curve. Now, this is swept along a path which is defined by another curve, which is called as a directrix curve. Then the area which will be swept by the curve is a surface, that I call as a swept surface. Now, sweeping is a concept which is not restricted only to surfaces. One can sweep a point along. In fact, whenever we define a curve, it is nothing but you have a point which is swept along a certain path. So, the area of swept, the distance which is swept by the point, the path which is swept by the point is what you call as a curve. Like when we represent a parametric equation x, y, z as a functions of u, you can say that u is a parametric this thing which is a sweeping direction. Then among the swept surfaces, there are a few which may be of which are commonly used, like most common is of course a linearly swept surface, where the directrix curve is a straight line. Okay. So, the direction along which you are sweeping a curve is basically, when it is a straight line, you call it as a linearly swept surface, or if the directrix curve is, let us say, arc or a circle, it is a circularly swept surface. But we need not restrict to these two directions only. I can take any arbitrary curve. I can take one arbitrary curve and sweep it along another arbitrary curve to obtain a surface. So, that you call as a generic. That means, you are extending the sweeping concepts to direction other than line and circle, which is there. But of the three, the special interest is of line and circle. Again, as I said, line and circle are the known forms. If if I can have a combination of, let us say, a free form and a known form, then I can use, let us say, I can take a free form curve and sweep it along line or a circle to obtain let us say a mixed form of surface. One direction is a known form, one parametric direction, another parametric direction is a free form. So, this is one of the very commonly used this thing. You may have seen, like when you go to a CAD package and try to model, let us say, a curve or a surface, even solid. Okay. For example, sweeping can be extended to solids. If I take, let us say, a cross sectional area, or let us say a surface itself, and sweep it along certain direction, then you get the volume which is swept is a solid. When you use a CAD package to model the component, what you are most of the time which you use is like a sweeping. You say extrude or revolve, they are all basically extrude and revolve are nothing but linear and circular sweep which you are using. Then you also see a sweep as an option in many of the packages, which basically represents the generic sweep which is shown here. So, this is one of the very easy, sweeping is one of the very convenient way to build objects, okay, and also convenient way to represent mathematically. So, we look at swept surfaces little more in detail. So, this is the third form. First form was the known form of surfaces, second is using sweeping to define. And of course, before I go to third form, here is like surfaces of known form can also be modeled as swept surfaces. Like we have looked at 5 known forms, they are all nothing but you can say they can also be modeled as swept surface. A plane is nothing but a line is swept along another line. That means both directrix and generatrix curve are straight lines. Cylindrical surface is, you have two combination, that is a line is swept along a circle which is there. So, in this case line is basically a generatrix and circle is a directrix, or it can be other way around. I can take circle as generatrix and line as a directrix. So, there are two combinations by which I can represent a cylindrical surface as a swept surface. Conical surface, a line is swept along a circle which is there. Spherical surface is a circle swept along another circle. Then toroidal surface is also a circle which is swept along another circle. Only thing is, both are in both the cases you have circle has generatrix and directrix, but only thing is there is a difference in terms of where these circles are situated and what is the radii of the circle that will define. So, one can also say that maybe though topology is different, a toroidal surface reduces to spherical surfaces for certain conditions, okay, when the radius and position of the circle matches. So, I can toroidal surface basically converges or becomes a spherical surface. So, all these surfaces can be, in fact, when we try to write mathematical representation, that is parametric representation of known forms, we make use of sweeping as a concept to do that, because it is easier to write in this case. Coming to the third form, we have seen the known form of surfaces, we have seen sweeping can be another method which can be used to represent surfaces, then whatever we discussed in our previous classes for free-form curves, like Hermite curves, Bezier curves, B-spline curves and NURBS curve, the same definition can be extended to surfaces. Okay. Like I can call it as a Hermite surface patch. Now, I am bringing the word patch. Patch is basically represents a surface which has fixed boundaries. Okay. That means, unlike just like we differentiate between a line and a line segment, okay, or a plane and a polygon. So, you also differentiate between a surface which extends infinitely and a surface which has definite boundaries, you call as a patch, a surface patch. So, one can define Hermite surface patch. I can use algebraic form to represent. If you recall, when we discussed the parametric curves, how many unknowns were there? So, we had a 12 unknowns. Now, here I have x, y and z are parametric equations, that is cubic in both u and w. So, if how many terms are possible for, like if I had like 12 unknowns in the case of parametric Hermite curve, that is a cubic curve. So, if I take, let us say, a Hermite surface patch which is both cubic in u and cubic in w, then for x itself I have 16. So, there are total 48 algebraic coefficients which can be used to represent an algebraic form of a surface. Now, that is only for what you call as a bicubic. It is not necessary that I should choose the same, you can say, a degree of polynomial for u and w. I can, for example, go up to cubic in u and I can restrict to only, let us say, square terms as far as w is concerned. So, you get a different combination, but again the one of the most combination is what you call as a bicubic, which is cubic in both u and cubic in w. So, if I am taking, let us say, a bicubic, this thing algebraic will have 48 unknowns, that is 16 unknowns for the x, 16 for y and 16 for z. So, y 16 that we have seen, you have terms like constant, you have u and w terms, you have u square, w square terms, u cube, w cube terms, then you have all the other combinations, u square w, u w square. If I take all combinations, then I have total 16 terms which comes, and for x, y, z total 48 algebraic coefficients which can be used. So, in fact, if when I write it in a matrix form, an algebraic form, I can simply use the same matrix which is used for parametric curves and just extend the surface. So, it is a very simple way to represent. We will see that later as we go along. Then there is a geometric form. When we discussed about PC curve, parametric cubic curve, geometric form, we gave again like 16 inputs, okay, that is start point, end point, and then the tangent vectors which are given, which also supply additional 6 values. Now, here you have to basically give 48 this thing, like if I am defining, let us say, a surface patch, then I will give 4 corner points. So, the 4 corner points will give me x, y, z values. So, 4 into 3, how many unknowns? So, I have 12 which are already covered as a part. Then whenever there is a surface which is a function of u and w, I can take a partial differentiation with respect to u and w. So, I have del x by del u and del y by del u, and this value, for example, at 4 corner points, if I take for example del x by del u as one of them, or del y by del u and del z by del y, all the points. So, I get how many more? Additional 24, okay, 12 for the points, okay, that is 12 for first differentiation, that is partial differentiation with respect to u, and another 12 for partial differentiation with respect to w, but that is not enough. So, I have to go for one more differentiation. So, you also use the values of del square x by del u del w. Okay. These are called as just like we had a points and tangent vectors. The same thing, del x by del u is called as a tangent vectors here too, but when I go for a second differentiation, those are called as a twist vectors. So, I can define a bicubic patch by defining 4 corner points, then tangent vectors, you have 2 tangent vectors, one along the u direction and another along the w direction, then the twist vectors. Those combination will give me enough inputs to solve algebraic. So, this we will see, but I am just trying to give you an overview of how to define this. Then we also looked at 4-point form. There are 4 points through which a parametric cubic curve passes. Here I define 4 by 4, that is 16 points. So, this is 2-dimensional matrix, okay, which you defining 4 by 4, and each consists of 3 points, 3 coordinates x, y, z. Okay. So, 16 into 3, again I have 48 inputs and I can this thing, but you have to again choose parametric values for the intermediate points, just like we did it in the case of parametric cubic curves. So, here also one has to choose. I can have n point form. Why did I put it as n point? Is for example, I can have a matrix of 5 by 4, so that the curve is quintic in one direction, okay, not quintic, quartic, and cubic in other direction, which is possible. So, one can choose any of these combinations as far as surfaces is concerned, since you have a parametric direction. Same thing can be extended to other points, like you have a Bezier surface patch, common is bicubic Bezier surface patch. In this case, m is 4 and n is also 4. So, you have 4 by 4 points, okay, that is 16 points, which will define the Bezier curves. Or I can have B-spline surface patch, you define by m and n, and you also define, like in the case of B-spline curve, we used additional variables. What is that? That is order. Like for example, when I use the value of k, suppose if it is k is equal to 4, it represents some form of equation. Now, when it comes to a B-spline surfaces, k can be same for u and w, or it can be different. I can choose that it is cubic in both the directions, or I can also choose a different this thing. So, this option also exists. When it comes to NURBS, you have the same definition as B-spline, but for every control point you also supply additional scalar value, which is called as a weightage, which will define this. So, once we know what are the parametric curves, extending them to parametric surfaces is not really difficult, it is quite trivial. And we can also use these for example, combination with sweeping. For example, I can take 2 Bezier curves, one is a generatrix curve and another is a directrix curve, and I can get a very generic swept surface, which is a part of this particular. Then when it comes to surfaces, you also have a few important surfaces which can be defined by boundary curves. Okay. Let us say if I have I am given 4 boundary curves, let us say for every surface patch the boundary is a curve. Okay. Now, these boundaries basically refers to fixing one of the parameter, like for example, if I say u is equal to 0, that means that becomes one of the boundary curve. When I say u is equal to 1, that is the second boundary curve. W is equal to 0 and w is equal to 1 are the 2 other boundary curves. So, if I just give input as my 4 boundary curves, I can define a number of ways the surfaces can be defined. That means, the surface basically interpolates the boundary in some manner. The 2 such interpolations which have come up in the last century are Kuhn's patch and Ferguson patch. Okay. These are surface patches which take 4 boundary curves to define. So, we look at the equation of this. This is also a very simple equation. Then I can also have what is called as a ruled surface, which takes only 2 boundary curves, 2 opposite boundary curves, and these are joined by straight lines. That means, you have a linear interpolation between 2 opposite curves. If I carry out a linear interpolation, then this is becomes a ruled surface. This is also of special interest in many applications. Then bilinear surface is when I have basically a ruled surface where the 2 boundary curves are straight lines. It is like a best way to define a bilinear surface is just by giving 4 points. Whenever I give a 4 points, they may or may not be coplanar. If they are coplanar, then you get a plane. That is a simple equation. Suppose if they are not coplanar, then you need to have a curved surface which interpolates all the 4 points, and one of the simplest way to do is to use linear equation in U and linear equation in W. So, if I am using U and W as a linear, then I have terms like constant term, U term, W term, and U into W. UW term also comes into picture. So, a bilinear surface is another special form. I think you may be aware of that ruled and bilinear surfaces are of special interest, particularly in NC machining for machining advantages, which is. So, this is a 4th way of defining, like first is known form, second is using the sweeping, third is extending the whatever we studied for curves to surfaces, fourth is I define boundary curves and try to interpolate in one of these ways. So, if I am using let us say any package which offers modeling of surfaces, it gives almost all these options. Okay. Now, you are free to choose what combination, one of the combinations of this, either I can use a standard form or sweep or this in order to build more complex geometries. Let us look at since we are already familiar with known form of surfaces, I can take up as a first sweep representation of surfaces as the first topic. And we have also seen that sweeping can also be used to represent known forms. So, it covers 2 of the category of surfaces if we study about this. Now, in a linearly swept surface, now we are trying to give mathematical definition. So far we were seeing only conceptually, like I have a curve. So, input to a linearly swept surface is a curve. What is this curve? This is a generatrix curve which is swept, and directrix curve is a straight line. So, I can directly specify what are the direction cosines along which it is swept and what is the distance by which the sweeping is done. By specifying these 2, I can define completely this thing. So, what is the input curve x, y and z, which are parameters of u. So, the resulting surface now is parametric in both u and w. So, this is the curve plus L is basically the x component of direction cosine multiplied by d, and w is the parametric direction which specifies this. So, this is now a surface equation with range between u and w ranging between 0 and 1, which is shown here. So, I can take let us say a curve and then sweep it along a direction to get a surface which is shown here. What is a parametric direction u, which is that of a curve, which is already known. The w represent the direction along which you are sweeping this particular thing. Another way to define this linearly swept surface is I take a curve which is x, y and z. Instead of specifying let us say a unit vector lmn and the distance by which it is swept, I can just specify 2 points. Whenever I specify 2 points in a space, I can always have define a vector completely. that is start point of a vector and end point of vector. This vector includes two things. I can get LMN, which are direction cosines. I can also get magnitudes. So, suppose if this point is x1, y1, z1 and here is a point which is x2, y2, z2, then I have x2 minus x1, y2 minus y1 and z2 minus z1. What do they represent? That represents nothing but LD. LD is x2 minus x1, MD is y2 minus y1 and ND is z2 minus z1. So, in this case the equation becomes x of u plus x2 minus x1 w, y2 minus y1 w and z2 minus z1 w. One very important thing is these points which are x1, y1, z1, x2, y2, z2 need not lie anywhere on the curve or anything. It can be anywhere in the space, as long as they, when once you say a vector, it can be anywhere in this thing. It can have any starting point, any end point, as long as magnitude and directions are the same. So, it really does not matter, it is the same vector which I am trying to represent. So, a linearly swept surface can be defined by a vector which has magnitude and direction, that is the direction along which you are sweeping, together with a generatrix curve. This curve can be simple curve, it can be a NURBS curve or any of the curves which one can think of. It can be closed or open curve, all options are allowed as far as linearly swept surface. Now, here is a simple, probably simplest example of linearly swept surface is a plane. I have a straight line which is, call it as a generatrix, then I have another straight line along which it is swept, which is directrix. So, if I sweep this particular thing along line, I should get a surface which is a planar surface. So, this is a planar surface which will be obtained, and you also, one should be very clear of the parametric directions, like the generatric curve which we used has a parametric u. So, this is u is equal to 0, it goes all the way up to u is equal to 1. Parametric direction is a w. So, it starts from w is equal to 0 and goes to w is equal to 1, and other corner represents u is equal to 1 and w is equal to 1. Now, one of the this form can also be used to represent a parametric equation of a triangle. See, for example, what are you specifying is I can define this entire plane by defining 3 points. A plane surface can be easily defined by specifying 3 points through which it is passing, like this may be a starting point. I have a second point, let me, in fact, I can go to this, like here is a starting point. I have another point which is, let us say a P3 or P2, whatever it may be. So, this gives me one vectorial direction. I have another vectorial direction which is P2 minus P1. By giving the 3 coordinates, that is x1, y1, z1, x2, y2, z2 and x3, y3, z3, I am able to represent completely the plane equation which we do. How do you do that? I know the 2 points, so I can get the parametric equation of line. Once I know the parametric equation of line, I can apply the linear sweep equation, because I know the other vector which is this thing, and do this. So, one of the ways to define is like given a 3 points P1, P2, P3 which are x1, y1, z1. So, parametric equation which are joining P1 and P2, we know that it can be written in the form of x1 plus x2 minus x1 u, y1 plus y2 minus y1 u, and this is. So, this is a parametric equation representing 2 of the points which goes from P2 to P1. Now, I can sweep this along a direction. What is the direction? That is P3 minus P1, okay, which is another direction which is given. So, this portion was the earlier equation. Now, I have to add LDW, isn't it? MDW and NDW. LD can be directly replaced by x3 minus x1, y3 minus y1 and z3 minus z1. So, if somebody says what is a parametric equation of a plane, then this is one of the ways to define. There are 3 points which are given, and here is I think this is not clearly represented. It is not just function of u, you should also have u and w, okay, and then this is the complete equation of a plane. Now, as I said, this can also be used to represent a triangle. If you have seen this, okay, like given 3 points, what should be the parametric equation of a triangle? If I use the equation as we discussed, I am getting actually 2 triangles, okay, that is this one and this 2. So, I can also differentiate like saying that there is one portion of this parametric equation represents a triangle. That means you can put additional condition in u and w in order to represent that. So, it can be very easily used to represent a triangle also. We will see what that condition is. How do you basically split a parametric surface so that you are concentrating on only one part of the surface, etc. So, this is a definition of a plane surface, a simplest of the linearly. Circularly swept surface can be also be defined by sweeping, let us say, a generatrix curve along a circle. Now, there can be many combinations of this, like I can choose that the curve is swept along one of the known axes x, y or z, which is simpler to represent. Other option is I have a curve which is you are sweeping along an axis which is lying in x y plane, okay, but it is not one of the standard x or y axis. Or I may have a situation where the axis is arbitrarily oriented with x, y and z axis. All combinations are possible, but often you choose one of the standard axis because it is easier to represent mathematically. If I want to sweep, let us say, a curve along an arbitrary axis, what I do is first I transform it such that the axis coincides with x, y or z axis using transformation, apply the sweeping and then do the reverse transformation, so that I get back the original equation. So, transformations together with sweeping can be used to represent a parametric equation of, let us say, a circularly swept surface along any arbitrary axis. Now, let us look at, I have a curve, let us say this is a parametric curve which is a function of u. This is a curve which is lying in xy plane. So, you have x and y which is a parametric of u. Now, this is swept along y axis. When I sweep it along y axis, I have x, y, z. Now, this capital X, y and z represent the coordinates of the surface which is obtained, which is a function of u and w. What happens to x coordinate of any point? As I am sweeping, the x coordinate actually moves towards the center, okay, then goes in the other direction and comes back. So, the variation is more in the form of a cos of a function. So, this is the x coordinate of the point of the curve multiplied by cos of this particular function. If I have any point which is a y coordinate on this particular curve, and if I am sweeping along the y axis, then y coordinate does not change, because height of this particular point, any point from the x axis remains same. So, y coordinate here will be same as that of y coordinate of the curve. Now, as I am doing that, initially this curve was in the xy plane, now it goes out of xy plane, okay, and at some stage this is in yz plane as it is sweeping, then it comes back to again xy plane. So, as x coordinate is changing as a function of cos, you have the other. So, this is like a circle. So, if I have a cos as one function, other function should be a sine, which is the x coordinate of the curve. So, just by using x of u and y of u and by adding additional terms, multiplying with additional terms, you are able to represent a simple circularly swept surface. Now, I can extend this to sweeping, let us say, circularly swept surface when the curve is swept along x axis or let us say a z axis. It is a simple one has to basically change these equations slightly, and one can do that as a part of this. But one thing which one has to keep in mind is also that one has to consider a positive sense of rotation and a negative sense of rotation. Otherwise, your parametric direction may change if I do not use properly the cos and sine functions in this manner. So, this is a very simple definition of, you can say, a circularly swept surface. Okay. One of the, of course, simple examples of sweeping is, let us say I have a straight line. This straight line is defined by 2 points. I can write down the parametric equation. So, I know x of u, y of u on this. Now, I substitute this in this to get basically a surface which is nothing but a conical surface, where u represent the this direction and w represent the circle which is basically obtained as a part of this. So, like when I sweep it, basically I get the swept surface which is a conical surface. So, this can be used to represent some of the known form of surfaces. For example, a cylinder can be very easily represented as a circularly swept surface. I can take a straight line, or another way is that I know the equation directly in a parametric form, I can put down. If I am given that axis of cylinder is z axis and radius is r and height is h, then I can directly write down the equation of this particular thing. But do you think this is like, given this kind of a thing, is it a unique kind of a thing? If this is the input, axis of cylinder is z axis, radius is r and height is h, is this equation unique, or there can be some changes? Like it, in this particular input, what is not shown is what is the starting point of, let us say, a cylinder, or where does the cylinder lie along z axis. Now, this is represented here. Suppose if I put w is equal to 0, then I get, sorry, this is z, I think this coordinate is z. So, if I put w is equal to 0, then I get z as 0. If I put w is equal to 1, then I get z as h. So, it is actually going from 0 to h, but cylinder may lie somewhere else. Okay. Now, suppose it may, I can have minus hw. So, if I have minus hw, that means it is the same cylinder which meets all these conditions, but lies somewhere else. So, this equation is not unique as far as this is concerned. Okay. I may have to give additional input in order to make it unique along the z axis, where it should be situated in the space. I have to give certain additional input. So, this is one of the simplest, I think, circularly swept surface which one can think of. Similarly, we can define a conical surface. Axis of the cone is given, which is z axis, and radius is given. There are two radii which can be given, either it can be a truncated cone or it can be a complete. So, in one case it becomes probably a 0. So, I have radius 1 as r1, radius 2 as r2, and then there is a height which is given. Now, I can write down the equation in this form. So, if I put, let us say, w is equal to 0, then I am getting one circle. If I put w is equal to 1, then I am getting another circle which is corresponds to r2 of that, and the height varies, height of the cone is given as h. So, this can be completely defined except for the, again, like the position which is not specified in this case. So, this is another example of circularly swept surface which is of a known form. Same thing can be done for spherical surface and a torus surface. If I take the generatrix curve and the directrix curve both as circles, I can represent an equation of a sphere or a torus very easily using the this particular form. Now, coming back to a generic swept surface, the input here is two curves. What are those curves? One is XU, YU, ZU, which is one of the curves which is given. Then you have another curve which has x prime, y prime, z prime, which is a function of W. So, this is one curve, let us say this I call as a generatrix curve, and here is a directrix curve which is given. Now, when I sweep it, what happens is basically you have to take, for example, you know two parametric directions. So, this is basically the area which will be swept can also be represented. The surface looks something like this. So, here is a curve, now this is swept along that. So, I have two parametric direction which is given to me, which basically represents a area which is swept by the surface. Now, in order to define this, this may look like a complex surface, but it is defined by just two curves. One is a generatrix curve. Curves are easier to represent than surface. So, complex surfaces can be easily modeled using curves which is given this. Many times this is used for what you call as a sweeping is used to define what is called as a mixed form, where one of the forms is either line or a circle, whereas the other is something which is a free form type of a curve. This is a very common in many of the CAD/CAM applications. Okay, so I think I will just stop it here because what we covered today is primarily an introduction to surfaces. What is left now is to look at two other forms, like how do we extend surfaces like whatever we discussed for parametric curves to surfaces. We will not go that much in detail because we have understood the concepts. So, we will put down the equation and try to look at a few common surfaces. Then we will also take up the surfaces which are defined by boundary curves, which is of special interest, which includes ruled surface or Ferguson patch, etc., which is there. And once that is over, then we will take up the solids. But overall, the subject of parametric curves and surfaces together forms, you can say, one entity, which one important aspect of geometric modeling. Sometimes you can call it as a surface modeling, as a broader area of a surface modeling which is used. Concepts can be extended to solids also, like I can have like just like I have a segment, curve segment or a line segment, I have a surface patch, then I can have a piece of solid which is bounded, it is called as a hyper patch. Okay. So, you have a Bezier hyper patch, I can have like tricubic Bezier hyper patch. This is defined by 4 into 4 into 4, 64 points. If I give 64 points as an input, I can define a Hermite hyperpatch or Bezier hyperpatch or B-spline hyperpatch or even NURBS hyperpatch can be. So, same concepts can be extended, but usually those are not very common, like representing a surfaces solids as a hyperpatches is not really this thing, because that kind of definitions are basically little too complex to deal with in terms of programming and others. And also, since a solid can be easily represented by a boundary surfaces, so I would like to deal with those complex solids also as consisting of 6 boundary surfaces which are easier to deal, okay, in one of the solid modeling representations which we will see later is this thing. But there are special ways to represent solids which we will also see as we look at, like constructive solid geometry or boundary representation, or there is a third method which is called as spatial enumeration methods, which are extensively used for certain applications. So, we look at those aspects when we come to solids, but this is just an introduction to parametric surfaces which we had. Now, I think it is a time for questions. Yeah.
What are the conditions that a toroidal surface reduces to a sphere?
What are the conditions that a toroidal surface reduces to this? I think let me go back to toroidal surface. So, how are you representing, let us say, a toroidal surface? Okay, I have an axis, and like how do I basically obtain, let us say, a toroidal surface? What is the generatrix and what is the directrix? Let us look at this. For example, these parametric directions which you are seeing, that I can call it as a generatrix. Then this is a directrix kind of a thing. Now, first thing is radius of bore should be same, generatrix and directrix, that is one thing. And another thing is generatrix curve, like if I take this particular curve, the generatrix curve which I have has the same center which is the center of the torus. So, suppose imagine that this circle moves towards the center as it starts moving. In fact, when it comes to a sphere, you need not actually take the complete circle, I can just take semicircle. Like how do I represent a spherical surface? I take a semicircle which is swept 360 degrees along this. Here you are taking a complete circle and do it. Okay. When I do that, when it comes to this thing, I can take only a semicircle. Even if I take circle, still I will get spherical surface only. There is no new thing which is. But though mathematically it reduces, but topologically they are very different. What do you mean? What do I mean by topology? Is that like a torus has a hole. Okay. An object with a hole is very different from an object which is completely a solid. Okay. Like a cube can be easily deformed, okay, to make, let us say, a sphere. So, they are in a way topologically they have the same. Those objects which do not have holes, in terms of geometric modeling terminology, you call that they have a genus which is 0. This is a genus which has 1, okay, like you have one hole which is there. So, that is usually represented as a genus. But it is not possible to basically deform this to a sphere without changing the topology and others. So, mathematically though it reduces, but topologically they are very different solids, surfaces or solids, you can say. I think that answers your question. That, yeah. Any other?
In bicubic basis surface, we need 16 control points. Control points represents the 4 control points of each curve.
Yeah, you can also say that. Okay. Your question is in a bicubic Bezier patch, 16 points are there. So, is it like every 4 combination represents a Bezier curve? Yeah, it is. In fact, it reduces to that. Like you take 16 points. So, this is actually 4 by 4, that is very important, not arbitrary 16 points. It is a 2-dimensional matrix of 3-dimensional points. In all the surfaces what you give is a 2D matrix of 3D points. Yeah, for example, if I take choose 4 points at a time, like 16 points are, let us say, represented as a matrix. If I take only one row, any specific row or column, it represents a Bezier curve. It definitely represents a Bezier curve.
Boundary representation,
Huh?
like Kuhn's patch, we are using the Kuhn's patch by the boundary curves.
Yeah, the only thing advantage of using, let us say, a Kuhn's patch kind of thing is, suppose I want to represent a surface. One boundary curve is a straight line, another boundary is a circular arc, third is a Bezier curve, fourth is, let us say, a B-spline curve. Still I can get a very good surface which interpolates this. So, you can use any combination, it does not prevent you to use a specific form. But I will come back later that one form can be converted to another. That is that can be very easily done. Like if, for example, if I take, let us say, a Bezier curve with 4 boundary curves, I can probably come back to one of the other forms. We will see that later. Okay. So, none of these are unique, one can be converted to another. Multiple ways of representing the same surface is possible. Like somebody can say that cylinder is a ruled surface, it is a ruled surface. Okay. If I take two curves which are circles and if I join them by, let us say, a straight line, then I get a cylindrical surface which is also a ruled surface. So, one can be converted to another. So, any other question?
Sir, in the case of a cone, you have said the line is a genetics and circle is directrix. So, in addition, whether we need any axis also, because if you will rotate a line into a circle.
See, once you say that directrix is a circle, circle has an axis. Circle cannot be defined without axis. So, the axis is automatically defined. The circle can be anywhere in the space, need not be x, y, y, z or z x plane or parallel to these planes. So, once I say that there is a circle anywhere lying in the space, it has an axis. So, you know the axis. So, you do not have to give specifically additional input as axis. Okay, I think we will stop.